Mars, the planet that has captured our imagination for centuries, is revealing more than we ever expected. With each new image sent from orbiters and rovers, we discover more secrets buried beneath its rusty surface. Dried up stream beds, strange cloud formations, and faint remnants of a time when Mars had lakes and seas. They are puzzle pieces pointing to a past when water flowed freely across the Martian landscape. From the search for microbial life to the possibility of human colonization, Mars remains the most likely candidate for the next frontier. In turn, the colossal Olympus Mons volcano, dormant for millions of years, may not be as silent as we previously thought. Could the red planet still be geologically active? And if so, what does this mean for our future explorations? Will Mars one day become our home? The red planet awaits, so let's get started. Mars has attracted human curiosity for centuries, and recent images from the red planet are changing our understanding of its environment and history. A research paper published in July this year reveals compelling evidence for water on Mars, allowing us to understand both its ancient past and its current state. Research shows that Mars, once warm and wet, had extensive bodies of water. Today, however, it presents a very different landscape, cold and desolate. This transformation raises crucial questions. Where did all the water go? According to a joint study by Hubble Space Telescope and NASA's Mars Atmosphere and Volatile Evolution, Mars is losing water at an alarming rate, especially as it approaches the Sun. The study shows that seasonal variations significantly affect the rate of these losses. At perihelion, the point of the orbit closest to the Sun, the planet experiences increased atmospheric heating, which leads to an increase in the concentration of water vapor. The study emphasizes that at perihelion, the rate of hydrogen and deuterium leakage increases dramatically, sometimes by a factor of 10 to 100 compared to aphelion, the farthest point from the Sun. These seasonal dynamics emphasize the complexity of the planet's atmospheric processes. John Clark of Boston University stated, "The whole atmosphere is very turbulent, heating up and cooling down on short timescales, even down to hours." During the warm season, water vapor is released and escapes into the upper atmosphere. Solar ultraviolet light plays a crucial role in this process by splitting water molecules into hydrogen and oxygen. Hydrogen, in particular, can escape into space if given enough energy, while oxygen, in turn, combines with Martian surface materials, giving the planet a reddish hue. An intriguing aspect of Mars' water loss is the changing ratio of deuterium to hydrogen. Over billions of years, as hydrogen escaped more easily, the ratio of deuterium to heavier hydrogen in the atmosphere increased. This ratio provides a glimpse into Mars' past and suggests that the red planet was once rich in water. Today, the DH ratio is about 8 to 10 times greater than on Earth, indicating significant losses over time. Despite significant losses, Mars still has substantial water reserves, mostly in the form of ice or in deep underground reservoirs. The research suggests that there may still be enough water on the red planet to create a global ocean several kilometers deep. The discovery renews hopes for future research as scientists seek to determine the potential for life on Mars, both past and present. At the same time, the search for life on Mars is taking an exciting turn thanks to the mystery of methane. Methane, a simple molecule consisting of one carbon atom and 4 hydrogen atoms, has also been detected in the Martian atmosphere in short seasonal bursts. These bursts raise critical questions about the chemical and biological processes occurring on the planet. NASA's Curiosity rover first detected a significant increase in methane levels in late 2013 and early 2014, 10 times higher than normal. Since then, Curiosity has recorded several spikes, mostly in late spring and early summer. This seasonal pattern suggests a dynamic process potentially related to environmental changes on Mars. The difficulty lies in determining the source of this methane. On Earth, methane is often produced by biological processes, particularly by microorganisms known as methanogens. However, modern Mars is a harsh, cold environment with no liquid water on its surface, making the presence of life as we know it highly unlikely. That the remaining liquid water exists mostly deep underground in microscopic cracks suggests that if life exists on Mars, it may be hidden beneath the surface, perhaps in these water-saturated pockets. The process that could lead to the formation of methane involves the interaction of liquid water with iron and magnesium-rich minerals such as olivine, a scenario reminiscent of chemical reactions on Earth. The sequence begins with water interacting with olivine to release hydrogen. This hydrogen can then react with carbon dioxide in the Fischer-Tropsch synthesis process to produce methane. However, in order for this process to occur, again, there must be liquid water beneath the surface of Mars. However, the geologic stability of Mars presents a problem. The planet is not geologically active to the same extent as Earth, so it's difficult to explain such rapid jumps in readings by the geologic process alone. This has led to speculation that methanogens, organisms that thrive in extreme environments, consuming hydrogen and producing methane as a metabolic byproduct, may be active on Mars. While the hypothesis that life exists beneath the Martian surface is compelling, it remains only a hypothesis. At present, no direct evidence of life or other biological byproducts has been found. In addition, there must be mechanisms to explain the rapid decomposition of methane in the Martian atmosphere. Methane is unstable and can degrade by processes such as ultraviolet dissociation and oxidation, which occur over very long periods of time. At this point, the observed patterns only indicate a complex interplay of environmental factors, and we still have much more to learn about what lies beneath the surface of the planet itself. Speaking of which, it's also impossible not to mention that Mars' thin and cold atmosphere offers an amazing spectacle. Clouds that form and drift across its skies, much like Earth's. For the past 20 years, the European Space Agency's Mars Express spacecraft has photographed countless Martian clouds and storms that provide the most detailed view of the planet's atmospheric phenomena, which are at once alien and so familiar. This summer, scientists at the German Aerospace Center compiled thousands of images taken by a camera aboard the spacecraft into Cloud Atlas, which provides an immersive virtual tour of the red planet's clouds. Unlike Earth, where clouds are composed mostly of water vapor, Martian clouds are composed mostly of carbon dioxide. The planet's atmosphere is so rarefied that any moisture present is a layer thinner than a strand of hair. However, despite the lack of water, these clouds form in surprising ways. One of the most striking examples is the Arisaman's elongated cloud, abbreviated AMEC, a massive formation that appears each spring near the southernmost of the planet's giant volcanoes. This elongated water ice cloud is formed when winds rising along the slopes of Arisaman's cool rapidly at high altitude and cause moisture to condense. What makes AMEC so unusual is its sheer scale. It can stretch 1,100 miles long and move at speeds up to 370 miles per hour. Although the cloud appears volcanic because of its location, scientists have ruled out the possibility of volcanic activity, attributing its formation to a complex interaction between wind and the Martian landscape. The appearance of Martian clouds is not limited to this region alone. The planet's atmosphere supports a range of cloud formations, including cloud streets, linear rows of clouds that resemble cumulus clouds on Earth. They're often observed in lowlands near the poles, such as Vastitas Borealis, and near volcanic regions such as Olympus Mons and Orissa Mons. Although they may resemble terrestrial clouds in shape, the conditions under which they form are quite different. On Earth, clouds form in a relatively dense atmosphere rich in water vapor. In contrast, Martian clouds form in a much thinner atmosphere with only traces of moisture. The planet's low atmospheric pressure means that even small changes in temperature can cause clouds to form abruptly. The thin atmosphere also allows for unique cloud structures formed by gravitational waves, oscillations caused by air trying to return to equilibrium after a disturbance in topography or weather patterns. These waves create distinctive ridge-like clouds similar to Lee waves on Earth that form when winds pass over mountains. Understanding how clouds form on Mars under such extreme conditions helps refine our models of planetary climate. But the neighborhood planet's quirks don't end there. Beneath the thin Martian atmosphere, an intriguing and rather strange phenomenon emerges during the planet's seasonal transitions: spider-like formations, officially known as Uraniform terrain. First spotted by orbiters in 2003, these sprawling web-like patterns stretch across the southern polar regions of Mars, covering sections of the surface in their outlandish, branching patterns. New experiments conducted at NASA's Jet Propulsion Laboratory and published this September have revealed the mechanism for creating these phenomena. Spiders are not the result of any biological process, but rather a geologic phenomenon related to Mars' unique interaction with carbon dioxide. The planet's atmosphere, composed mostly of CO2, experiences extreme temperature fluctuations between Martian winter and spring, especially at the poles. During the cold winter months, carbon dioxide freezes right to the ground, forming a layer of dry ice on the surface. As spring arrives, the Martian surface begins to heat up. But the unexpected twist is the CO2 ice doesn't just melt. Instead, it undergoes a process called sublimation, completely bypassing the liquid phase and transforming from solid ice to gas. This rapid transformation leads to a buildup of gas below the surface, trapped beneath the still frozen upper layers of ice. Eventually, this gas pressure in the trap reaches a critical point and it escapes through weak spots in the surface, creating channels for escape. These channels leave behind characteristic spider-like patterns. The gas violently bursts outward, rising into the atmosphere and leaving indelible marks on the landscape below. These scars can stretch for more than a kilometer, with hundreds of branching legs diverging from the eruption sites. Experimenters at JPL have successfully recreated this process under controlled conditions. Using the Dusty camera, a device designed to simulate the harsh environment of another planet, scientists replicated the formation of the uraniform terrain by cooling carbon dioxide into dry ice inside simulated Martian soil. As the ice heated up, the gas erupted and left behind those very patterns, confirming a theory of their formation known as the Kiefer model. This process is unique to Mars, primarily because the planet uses CO2 rather than water ice for most of its atmospheric and surface activity. Such formations are not a curious geologic phenomenon. They provide a glimpse into how Mars's climate has changed over time. The distribution of uraniform terrain is concentrated in certain regions near the South Pole, suggesting that certain conditions such as temperature, surface composition, and seasonal variations are necessary for their formation. This may be related to historical changes in the Martian atmosphere, providing insight into how Mars's climate has changed over millennia. Well, as scientists continue to explore these formations, uraniform terrain can help us better understand CO2 cycles and the role it plays. The spiders of Mars, though strange and alien to our eyes, reveal the powerful forces at work beneath the planet's seemingly calm surface, forces that continue to shape its landscape with each passing season. Now let's delve a little more deeply into the topic of the Martian surface, or more accurately, beneath it. Mars, a planet long thought to be geologically inactive, is showing signs of activity deep beneath its surface. New data from Martian orbiters and seismic measurements from NASA's InSight mission indicate that something big is happening on the red planet, particularly beneath the volcanic Tharsis region, home to the previously mentioned Olympus Mons, the solar system's largest volcano. At 13.6 miles high, Olympus Mons surpasses any volcano on Earth. Its size is breathtaking, but the real mystery lies beneath. New gravity maps of Mars have revealed a huge, slowly rising plume of magma that stretches more than 1,000 miles across and deep beneath the surface. This reservoir, a molten pool of enormous energy, is pushing upward, suggesting that Mars may not be as geologically calm as previously thought. For millions of years, this one and its neighboring volcanoes, Ascarius Mons, Arsia Mons, and Pavonis Mons, have been dormant. But the presence of such huge magma plume begs the question: could Olympus Mons be preparing for another eruption? According to researchers, the mantle plume found beneath the Tharsis bulge is unequivocally slowly but steadily rising. This brings heat and molten rock closer to the surface, which could lead to renewed volcanic activity in the future. Although no immediate eruptions expected, the gradual movement of magma through the planet's interior indicates that the planet remains geologically active. Gravity anomalies detected by the orbiters show variations in the distribution of mass beneath the surface, with weaker gravitational forces corresponding to a larger and less dense magma basin beneath Tharsis. These variations show that Mars' internal structure is much more complex than previously thought. An uneven distribution of material could be the cause of upcoming volcanic events. The magma rise beneath Tharsis is not just about Olympus Mons. It is about the entire volcanic system that encompasses this region. The 3,000-mile-wide, 4-mile-high Tharsis bulge is a massive plateau with volcanic peaks scattered across its surface. The upward movement of the mantle plume could trigger localized volcanic events in areas that have not seen activity in millennia, gradually changing the planet's landscape. But why now? What caused this deep magma basin to start rising after such a long lull? According to current theory, this magma plume formed slowly over millions of years, building up pressure beneath Mars' crust. Over time, the planet's internal dynamics, its cooling core and mantle, may have shifted enough to allow the plume to rise. If Mars is still geologically active, this could have significant implications for the planet's long-term suitability for life. A planet with internal heat could support subsurface liquid water, perhaps the most important factor in the search for life. This region, with its ancient lava flows and possible future activity, could be a key location for research in the search for signs of past or present life on the planet. And lastly, a couple of more fresh news spots about the planet. Mars continues to reveal its secrets through the eyes of orbiters and rovers, and among the most exciting of recent discoveries is an ancient formation that has scientists and the public intrigued: a smiley face edged onto the surface of the red planet. This emoticon-like feature, captured by the European Space Agency's ExoMars Trace Gas Orbiter, is not just a geologic curiosity. Unexpectedly, it could be another potential clue to understanding Mars' watery past and perhaps its suitability for life. This so-called smile is a remnant of an ancient lake that dried up billions of years ago. The face itself consists of chloride salt deposits, arranged in such a way it gives the impression of a grin, complemented by two meteorite eyes. But it wasn't its bizarre shape that caught the scientists' attention. These deposits of chloride salts are important because they were left behind after the evaporation of water on the planet. Billions of years ago, Mars, like Earth, had lakes, rivers, and perhaps even shallow oceans. But with abrupt climate change, probably due to the loss of the magnetic field, the atmosphere thinned and the water gradually disappeared. This transformation left only traces of the planet's wetter past. Researchers speculate that these salts may have preserved signs of ancient microbial life, creating conditions in which extremophiles could survive as the planet dried up. In fact, the very nature of these salt deposits makes them ideal objects for study. Salt has preservation properties that can preserve biological materials for billions of years. If microbes did exist on Mars, well, their remains may still be trapped in these ancient sediments, awaiting discovery by future missions. In other fresh images, NASA's Curiosity rover made history by taking the first ever photo of Earth and the Martian moon Phobos in the same frame, a striking visual reminder of our place in the solar system. The image shows our home planet as a tiny dot visible from millions of miles away next to the larger of Mars's two moons. These images inevitably make us think about the vast distances between the planets and the fact that the ongoing exploration of the red planet is sure to bring even more breathtaking images and groundbreaking discoveries to look forward to. In the meantime, stay tuned and stay curious. There is a phenomenon in the field of astronomy that has intrigued and puzzled scientists for years. Hidden behind the glittering veil of the Milky Way, in the region of space we call the avoidance zone, there exists a gravitational anomaly so vast, so powerful, that it tugs at the very fabric of our universe. This is the Great Attractor. Although invisible to our telescopes, its gravitational influence is so great that it affects the motion of galaxies hundreds of millions of light years away, including our own Milky Way. But what is the Great Attractor? Is it a supermassive black hole? A colossally dense cluster of galaxies? Or something else entirely? And more importantly, what does its existence mean for us, for our galaxy, and for the future of the universe? In this video, we'll explore these questions, delving into the impact of the Great Attractor on our galaxy and the challenges scientists face in observing this elusive region of the cosmos. We'll also travel to the recently discovered South Pole Wall, a vast cluster of galaxies stretching at least 700 million light years into space, and its intriguing connection to the Great Attractor. So, will we eventually be consumed by this anomaly, or does it still serve another purpose in the grand scheme of the universe? Let's find out. About 4 decades ago, astronomers used the Parkes telescope to peer through the dust of the Milky Way. They discovered that our galaxy is traveling through space much faster than expected, Imagine, our Milky Way is traveling through space at 2,500 times the cruising speed of an airliner, 55 times the escape velocity of the Earth, and even twice the escape velocity of the galaxy itself. But where does such movement come from? Here's the mystery. The theory of our origin, based on the Big Bang, tells us that every point in the universe should fly apart from every other point. However, the galaxies on either side of us should be moving at the same recessional velocity, which should not result in net motion in the Milky Way reference frame. Net motion can arise from nearby clusters in the distribution of matter, such as a massive cluster of galaxies. The additional gravitational attraction of such a cluster of galaxies can slow down and even reverse the expansion of the universe in its immediate vicinity. But in the direction of motion of the Milky Way, such a cluster is not obvious. There is an excess of galaxies in the general vicinity and an excess of radiation visible in X-ray telescopes, but nothing that somehow seems large enough to explain the results. So what are we observing? A superdensity of pure dark matter? Or is the current theory of the origin of mass and motion wrong? Astronomer Alan Dressler of the Carnegie Institution used the first explanation, dashingly calling the missing concentration of matter the Great Attractor. But the mystery of the Great Attractor continues to baffle us. Despite our best efforts and the discovery of new galaxies, galaxy clusters, and new threads in the cosmic web, we still haven't found enough to explain our motion. The Great Attractor remains a mystery, pulling in our Milky Way and leaving us with more questions than answers. So over a vast expanse of space, some 220 million light-years away, there is a gravitational anomaly known as the Great Attractor. This region of space, located within the Laniakea supergroup, has such an enormous gravitational pull that it affects the motion of galaxies for hundreds of millions of light years, including our own Milky Way. But what is a great attractor? The term Great Attractor was coined to describe its gravitational influence, but it is not actually a single entity, but rather a region of space with a higher concentration of mass. This mass consists not only of visible matter like stars and galaxies, but also dark matter, an invisible and mysterious form of matter that by some estimates makes up about 85% of the mass of the universe. Understanding the Great Attractor is like putting together a cosmic puzzle. We know it's there because we can observe its gravitational effects, but we cannot see it directly because it's located in the avoidance zone, a region of space hidden by the dust and stars of the Milky Way. Despite these challenges, scientists have made significant progress in studying the Great Attractor. They have used various techniques, such as X-ray, infrared, and radio observations to peer through the dust and gas of the Milky Way and gain insight into this mysterious region of space. According to information to date, the Great Attractor is part of a larger structure called the Norma Cluster, which is one of the most saturated known galaxy clusters. It is in this cluster that the center of the Great Attractor is located. The Norma Cluster is moving toward the Great Attractor at an astounding speed of about 1,340 miles per second. So as we've said, the gravitational influence of the Great Attractor extends over a region of space spanning hundreds of millions of light years. This region, known to us as the gravity well of the Great Attractor, includes our own local group of galaxies, which is attracted to the Great Attractor at a rate of about 370 miles per second. Observing the Great Attractor is not easy. You can't just point a telescope at it and look. The main problem is its location. The Great Attractor is located behind the Milky Way in a region astronomers call the avoidance zone. The zone is filled with dust and stars, making it difficult to observe the Great Attractor directly. However, it hasn't stopped astronomers from trying to unlock its secrets. They have to be creative in their methods, using different types of observations to peer through the dust and gas of our own galaxy. One of the main methods used is the observation of the 21-centimeter-long neutral hydrogen line. This faint line can be detected by sensitive radio receivers, allowing astronomers to see thousands of galaxies in blind surveys. The advantage of using radio waves is that they can pass right through the dust layer in the Milky Way, making our galaxy invisible. In the late 1990s, a group of astronomers began using the Parkes multi-beam receiver, an innovative instrument located in New South Wales. This receiver's unique sensitivity and field of view allowed increasingly sensitive radio surveys of the sky. These surveys, combined with data from new infrared surveys by the Hubble Space Telescope, have allowed astronomers to confirm the presence of nearly 80% of the galaxies found in the avoidance zone. The remaining 20% are too deep in the Milky Way to be confirmed with any existing optical or infrared telescopes. The zone of avoidance is a fascinating region of space. It's like a curtain that hides part of the universe from our view. But with the help of advanced technology and innovative techniques, we've been able to peek behind this veil and see hidden galaxies. The use of infrared surveys has been crucial. These surveys have allowed us to confirm the presence of galaxies that were previously hidden. It's like having a torch that can illuminate the dark corners of the universe. As we continue to explore and map the universe, a colossal structure known as the South Pole Wall has been discovered in the vast expanse of space. This wall, a veil of galaxies, dust, and gas, extends for at least 700 million light-years. It is so massive that it disrupts the local expansion of the universe. However, this huge structure, like the Great Attractor, remains hidden behind our galaxy, the Milky Way. It stretches from the constellation Perseus to the northern hemisphere to the constellation Apus in the far south. But despite its proximity and size, it's long gone unnoticed, hidden in a darkened sector of the southern sky. The South Pole Wall is a recent discovery announced by an international team of astronomers led by Daniel Pomeroy of the University of Paris-Saclay and R. Brent Tully of the University of Hawaii. The discovery was made possible by measuring the distances to 18,000 galaxies 600 million light-years away. Although the South Pole Wall is not visible to us, we can observe its gravitational effects. In an expanding universe, distant galaxies fly away from us. However, galaxies between Earth and the South Pole Wall are moving away from us a little faster than they should be, drawn outward by the huge clump of matter in the wall. Conversely, galaxies beyond the wall move outward more slowly, held back by the gravitational resistance of the wall. The South Pole Wall is an important part of our local universe. It's as large as the Great Wall of Sloan, but is twice as close to us. However, it still goes unnoticed because of its hidden location in the southern part of the sky. It is connected to the larger structure of the Laniakea supergroup, which includes the Great Attractor. All these structures are interconnected, affecting the local expansion of the universe and the motion of the galaxies. The Great Attractor, the South Pole Wall, and other such structures shed light on another enduring cosmic mystery: where we are going. Imagine you're floating down a river in a small boat without oars. The current of the river, like the gravitational pull of these cosmic structures, guides the motion of your boat. No matter how hard you try to control your boat, the current pull is too great, ultimately determining your path and speed. Similarly, our galaxy is like a small boat in a cosmic river, guided by the gravitational pull of massive structures such as the South Pole Wall and the Great Attractor. The future of our understanding of the universe and the Great Attractor lies in further research. Astronomers from Australia are leading several pioneering projects. The 2MTF survey, initiated by Castro, has already made a significant progress. Using the Parkes telescope, this survey calculates distances to galaxies, shedding light on the structure and motions in our neighboring universe. But the research doesn't end there. The upcoming Wallaby study, due to begin later this year, promises to push the boundaries of our understanding even further. Using Australia's advanced CSIRO-SKA Pathfinder, or ASCAP telescope, this survey will allow us to probe deeper into the radio universe. In tandem with these radio surveys, the Australian Astronomical Observatory and ANU are embarking on a new optical survey called Taipan. This project will focus on elliptical galaxies, allowing us to travel to more distant regions of the universe. As research continues, our understanding of the universe is being challenged. Theorists are beginning to question the validity of the space-time metric we currently use to describe the universe. There's even talk of changing the general theory of relativity on large scales. As we look out into the cosmic expanse, we can't help but ponder the future of our universe. What does the accelerated expansion of the universe due to dark energy mean for us, for the Milky Way, for our Great Attractor, for the countless galaxies dotting the cosmic landscape? The universe is not static. It is expanding, and this expansion is accelerated by a mysterious force called dark energy. This force is so powerful it stretches the very fabric of space-time, causing galaxies to diverge from each other. But what does this mean for the future of galaxies and superscales? And what role does the Great Attractor play in this cosmic drama? Despite the expansion of the universe, the Great Attractor continues to exert gravitational influence on the galaxies surrounding it, including our Milky Way. So back to the burning question: will the Great Attractor swallow us up? The answer is no. Despite its enormous gravitational pull, the Great Attractor is not a cosmic monster ready to swallow us whole. As the universe expands, its gravitational influence will weaken. In the distant future, as the expansion of the universe continues to accelerate, galaxies that are currently attracted to the Great Attractor may begin to move away. The gravitational bonds holding the superclusters together will weaken, and these massive structures may begin to disintegrate. The future of the universe is a vast, ever-expanding cosmic sea with galaxies like islands drifting in the cosmic ocean, slowly moving away from each other. The Great Attractor, once a formidable gravitational anchor, will eventually lose its power over the galaxies around it. For centuries, Venus has been a planet of intrigue and mystery. Known as Earth's twin, it shines in our night sky, yet remains one of the most hostile places in our solar system. Back in 2021, the ESA JAXA Bepi-Colombo mission made a fleeting visit to Venus. However, it was in April of this year that a reanalysis of the data revealed unexpected findings. There were oxygen and carbon ions coming out of the planet's upper atmosphere. These heavy ions, which are normally slow and difficult to move, have been found accelerating at unexpected speeds. Scientists still can't figure out what forces are behind this phenomenon. Is it an electrostatic wind, or perhaps centrifugal processes have intervened? Venus has long been an object of exploration. Early missions like Mariner 2 confirmed the absence of a magnetic field, and Venera 4 gave us our first glimpse of its thick, toxic atmosphere. Pioneer Venus Orbiter and Venus Express mapped previously unknown regions, but many questions remain. So how did Bepi-Colombo allow a more detailed picture to emerge? How did Venus lose its water? And why is its atmosphere so different from Earth's? And most importantly, could we ever survive on Venus? Today we learn about the harsh realities and the tantalizing possibilities of setting up a home with our mysterious neighbor. Venus's atmosphere is a complex and fascinating study. Composed mostly of carbon dioxide and sulfuric acid clouds, it starkly contrasts the life-sustaining air we breathe on Earth. At the surface, the pressure is 90 times the Earth's pressure, and temperatures, they reach 869 degrees Fahrenheit. Now, this incredible heat is the result of the greenhouse effect, trapping solar energy in the dense, opaque atmosphere. Our understanding of this hostile environment began with early missions like Mariner 2, which first confirmed extreme surface temperatures. The Venera 4 spacecraft made deep measurements, revealing a dense carbon dioxide atmosphere and the presence of sulfuric acid clouds. Pioneer Venus Orbiter mapped the upper atmosphere, showing the dynamism of Venus's weather systems and the presence of thunderstorms. And then came Bepi Colombo. During flybys, the spacecraft penetrated previously unexplored regions of Venus' magnetosphere. Its instruments detected positively charged oxygen and carbon ions being carried away from the upper atmosphere. These findings were unprecedented because heavy ions like these are usually slow-moving and difficult to dislodge. The output of these ions testifies to the complex interaction between the solar wind and the atmosphere of Venus. Unlike the Earth, which has a strong intrinsic magnetic field, Venus only has a weak induced magnetosphere created by the interaction of the solar wind with its atmosphere. This makes Venus more susceptible to atmospheric destruction by solar particles. Now for the most startling fact, a comparative study of water loss by Earth and Venus was conducted. Both planets, according to scientists, started with the same amount of water. However, Venus's proximity to the Sun and the lack of a protective magnetic field allowed solar radiation to break down the water molecules in its atmosphere. Hydrogen, being the lighter element, escaped into space, while oxygen remained, contributing to the dense carbon dioxide atmosphere we see today. In contrast, Earth's strong magnetic field has protected its atmosphere, preventing significant water loss and enabling the development of life. This striking difference emphasizes the importance of magnetic fields for planetary habitability. Understanding the atmospheric mysteries of Venus not only provides a glimpse into its past, but also serves as kind of a precautionary measure for us here on Earth. A bit of history for context. Space missions have been the cornerstone of our understanding of Venus. Each mission, with its unique capabilities, has contributed to unraveling the planet's mysterious environment. The journey began with Mariner 2 back in 1962, the first successful mission to another planet. Mariner 2 confirmed the extreme surface temperature of Venus and established the absence of its own magnetic field, setting the stage for future explorations. In 1967, the Soviet probe Venera 4 made the first direct measurements of Venus's atmosphere. It detected a dense carbon dioxide atmosphere with clouds of sulfuric acid and provided us with the first data on the ionosphere. The Pioneer Venus Orbiter, launched in 1978, began systematically mapping different regions of Venus's atmosphere, providing extensive data on its composition and dynamics. It confirmed the presence of heavy ion streams and helped identify the boson and magnetosheath formed by the interaction of the solar wind with Venus's atmosphere. The Venus Express mission, launched in 2006, built on those results and used the space plasma and energetic atoms analyzer to study ion emissions in detail. It measured the absolute number of hydrogen, helium, and oxygen ions escaping, providing crucial insights into atmospheric loss processes. In August of 2021, Bepi Colombo, a joint mission of ESA and JAXA, made its second flyby of Venus. This spacecraft penetrated previously unexplored regions of Venus's induced magnetosphere. The mass spectral analyzer and ion analyzer detected cold oxygen and carbon ions escaping from the atmosphere. Ions were detected at a distance of about 6 planetary radii in a previously unexplored region. Among the departing ions were O positive and C positive, the latter being the first to be seen escaping from Venus's atmosphere. This indicates a complex interaction between the solar wind and the induced magnetosphere of Venus. Unlike Earth, which has a strong magnetic field of its own, Venus has only an induced magnetosphere formed by the interaction of the solar wind with its atmosphere. The induced magnetic field is comet-shaped, creating a magnetosphere in which solar wind particles are slowed down and heated. Bepi Colombo's observations of the ion ejection mechanisms in this region have provided new insights into the processes that are inexorably destroying Venus's atmosphere. Understanding these mechanisms is critical to understanding the evolution of Venus's atmosphere, in particular, the process of losing its initial water concentration. The quest to understand Venus involves not only studying its hostile environment, but also looking for the potential for life in the most unexpected places. Even in Venus's harsh atmosphere, scientists are searching for the fundamental components of life. High-tech experiments aim to study Venus's atmosphere in search of evidence of life-supporting molecules. The discovery of phosphine gas in the upper atmosphere of Venus in 2020 has sparked intense interest. On Earth, phosphine is associated with biological processes, leading scientists to wonder whether similar processes could occur on Venus. However, the harsh conditions on Venus complicate this search. Because of the extremely high surface temperatures and immense atmospheric pressure, any potential life forms must be incredibly survivable. Despite these difficulties, the search continues. NASA's upcoming missions, Da Vinci and Veritas, aim to delve deeper into the atmosphere and surface of Venus. The Da Vinci mission will focus on measuring atmospheric gases, including noble gases and other elements, from the top of the atmosphere to the surface. These data will help scientists build new climate models and study the chemical composition of the atmosphere in more detail. The Da Vinci lander will provide unprecedented insight into the composition of the atmosphere and possibly detect molecules that may be precursors to life. These measurements will be critical to understanding the habitability potential of Venus and other similar exoplanets. The Veritas mission, on the other hand, will create high-resolution maps of Venus's surface. By studying the planet's geology and topography, scientists hope to discover signs of past volcanic activity and water flows, which are important clues to understanding Venus's history and its potential to harbor life. This detailed study of Venus's surface and atmosphere helps astrobiologists improve their models of planetary habitability. Venus provides an instructive example. Despite its similarities to Earth, its environment has taken a radically different path. Understanding these divergent evolutionary paths can help us in our search for habitable worlds beyond our solar system. Venus and Earth, often referred to as sister planets, have striking similarities in size, mass, and composition. However, their environmental and atmospheric conditions could not be more different. Venus's atmosphere consists mainly of carbon dioxide and nitrogen, with clouds of sulfuric acid creating a dense toxic blanket. Earth's atmosphere, in contrast, is composed of nitrogen and oxygen, supporting a variety of life forms. Atmospheric pressure on Venus is 90 times higher than Earth's, which is equivalent to being underwater at a depth of 1,000 yards. The greenhouse effect is extreme here. Solar radiation penetrates through dense clouds, heating the surface, but a dense atmosphere of carbon dioxide traps this heat, resulting in surface temperatures of around 869 degrees Fahrenheit. On Earth, on the other hand, the greenhouse effect maintains temperatures suitable for life, but maintains a delicate balance. There are also several fundamental differences between the two planets in addition to their proximity to the Sun. Earth has a relatively fast rotation period of 24 hours and a stable axial tilt, which promotes even heat distribution and supports seasonal changes. Venus, on the other hand, rotates slowly, in the opposite direction of most planets in the solar system, with a rotation period of 243 Earth days. This slow rotation and lack of significant axial tilt results in minimal temperature fluctuations between day and night. The slow retrograde rotation contributes to the planet's extreme weather patterns and thick super-rotating cloud layers that circle the planet every 4 Earth days. These clouds reflect a significant amount of sunlight, giving Venus a bright appearance, but also trapping a tremendous amount of heat. Geologically, both planets have volcanic landscapes, but whereas on Earth tectonic activity recycles carbon and supports a diverse climate, the surface of Venus is dominated by vast volcanic plains and high-altitude regions. The lack of tectonic plates on Venus means that heat is stored beneath the crust until it's released by catastrophic volcanic events, reshaping vast areas of the planet. The presence and loss of water are crucial factors in the different evolutionary paths of these planets. Measurements of the ratio of deuterium to hydrogen in Venus's atmosphere indicate that the planet once had a significant amount of water. The high ratio suggests that the lighter hydrogen was lost over time, while the heavier deuterium remained, indicating a historical loss of water. The different evolutionary paths of Venus and Earth give rise to the realization that the planet may be habitable. Venus's proximity to the Sun probably created a greenhouse effect that vaporized all the oceans and led to its current inhospitable state. Earth, which is at a moderate distance from the Sun and has a protective magnetic field, has retained liquid water and a stable climate favorable to life. As we enter a new era of space exploration, several ambitious missions are about to reveal more of its secrets. ESA's Envision method, already scheduled for launch in 2031, is designed to provide a comprehensive understanding of Venus from its core to its outer atmosphere. Envision will build on the discoveries of previous missions, such as Venus Express, which have hinted at volcanic activity, and will offer a detailed understanding of Venus's geological and atmospheric processes. Envision will carry an extensive suite of instruments designed for a comprehensive study of the planet. Synthetic aperture radar will map the surface at resolutions of up to 10 meters, revealing details about surface texture and geological activity. Its subsurface radar sounder will penetrate up to a mile below the surface, searching for underground structures and layers. 3 spectrometers, VenSpec-U, VenSpec-H, and VenSpec-M, will analyze trace gases, look for volcanic gas plumes, and map surface composition. The Gravity Radiological Experiment will use radio waves to study the planet's internal structure and atmospheric properties. Envision will help unravel how geologic processes such as volcanism and tectonics affect the planet's atmosphere and climate. This integrated approach will provide critical data to answer long-standing questions about Venus's past and present geologic activity and the dynamics of its atmosphere. India's Chakrayan mission, led by the Indian Space Research Organization, is another important addition to the exploration of the planet. Planned for launch in the early 2030s, the probe will study the atmosphere and surface of Venus using a suite of advanced instruments. Instruments will be installed on board to analyze cloud layers, atmospheric composition, and features of the planet's surface. Using infrared and ultraviolet cameras, the spacecraft will study the dynamics of Venus's dense cloud cover and the interaction of the atmosphere with the surface. One of Chakrayan's main goals is to understand the sulfur cycle on Venus, which plays a crucial role in the chemistry of its atmosphere. By studying the distribution of sulfur compounds and their interactions with other elements, she will contribute to our understanding of the complex atmospheric processes on this yellow planet. These missions have the potential to revolutionize our understanding of Venus. By combining data from Envision, Chakrayan, Da Vinci, and Veritas, scientists will have a complete picture of the geologic and atmospheric evolution of Venus. These missions will provide crucial data on volcanic and tectonic activity, atmospheric composition, and surface interactions, helping to build a detailed picture of the planet's past, present, and even future. Data from these missions will also help us understand planetary habitability and the conditions necessary for life. By studying Venus, we'll be able to improve models of atmospheric and geologic processes, which will improve our ability to identify habitable environments on exoplanets. Looking to the future, the ultimate goal of Venus exploration is to pave the way for future human missions. Although the planet's extreme conditions pose significant challenges, advances in technology and a better understanding of the environment may one day make planetary exploration possible. Future missions could include robotic explorers, capable of withstanding the harsh conditions of Venus's surface and then developing habitats that would protect humans from the intense heat and pressure. These habitats would then be equipped with advanced life support systems, allowing for longer stays on the planet and more in-depth scientific research. Exploring Venus is not just about exploring our nearest neighboring planet. It's about pushing the boundaries of what's possible in space exploration. By overcoming the challenges of Venus, we'll be able to develop the technologies and strategies that are needed to explore other extreme environments in our solar system and beyond. Imagine a place where the boundaries of reality blur, where the very fabric of the universe is stretched, and the unknowable becomes known. This is not a science fiction world, but a reality created deep underground, beneath the border between France and Switzerland. Here is the largest machine ever built by mankind, the Large Hadron Collider. It is a marvel not only of engineering, but also of ambition, and a testament to our quest to understand the universe at the most fundamental level. But could this device, designed to unlock the mysteries of particle physics, also be the key to opening portals to other dimensions? The idea of spatial portals may conjure up images of sci-fi gadgets and interstellar travel. Still, here at the European Organization for Nuclear Research, also known as CERN, they represent the gateway to revolutionary discoveries. Here, the concepts of space, time, and reality are intertwined thanks to the high-speed collisions of subatomic particles. This is not just a story about complex mechanisms and theoretical physics. It's a journey into the heart of what makes our universe move, made with the planet's largest and most powerful particle gas pedal. As we go deeper, we learn how these experiments not only challenge our understanding of the universe, but change it. CERN is nestled among the beautiful landscape of Europe, where the serene tranquility of nature meets human curiosity. The European Organization for Nuclear Research, the epitome of global cooperation, is home to scientists and engineers seeking to unravel the layers of our reality. CERN was founded in 1954 to unite nations in the pursuit of scientific knowledge, and has grown to become the world's largest particle physics laboratory. Here, more than 10,000 minds from over 100 countries converge to push the boundaries of human knowledge. The heart of the organization's research is located deep underground, the Large Hadron Collider, or LHC. This outstanding example of human ingenuity spans 17 miles, a circular tunnel in which the most advanced scientific experiments ever conceived are conducted. As the most powerful particle gas pedal on Earth, the LHC allows physicists to recreate the conditions that occurred moments after the Big Bang. By accelerating particles to near light speed and colliding them with each other, the LHC helps us explore the fundamental particles that are the building blocks of the universe. But CERN's role goes beyond particle physics. As a center of global scientific research, it is also a hotbed of technological advances, innovations developed here, such as the World Wide Web, have fundamentally changed our world, illustrating how basic research by scientists has gone beyond the laboratory to impact society as a whole. This institution is more than a laboratory. Using the universal language of research and discovery, the European Organization for Nuclear Research brings people and countries together, demonstrating that our quest for knowledge knows no boundaries. If we delve deeper into the basic purpose of the Large Hadron Collider, we find that its true scientific excellence lies in the fact that it allows physicists to test and extend several fundamental theories of particle physics. This machine is as much about brute force as it is about precision and the subtle nuances of particle behavior at incredibly high energies. The standard model of particle physics, developed in the middle of the 20th century, describes the forces and particles that make up our universe. However, it is not complete. The LHC is a unique environment where particles collide at high enough energies to detect phenomena that can either confirm or refute this model. One of the key aspects of the research is the study of supersymmetry, the theory that every particle we know has a heavier superpartner. These partners, if they exist, could unlock many of the mysteries of the universe, including the nature of dark matter. The LHC also plays an important role in investigating the validity of string theory, a branch of theoretical physics that attempts to reconcile gravity with quantum mechanics. It suggests that point particles in particle physics can be replaced by one-dimensional strings. The vibrations of these strings appear to us as different particles. The energy levels achieved in this giant laboratory allow us to explore these ideas, potentially creating new particles predicted by string theory. But beyond the tangible, the LHC has entered the realm of what many consider science fiction. The idea of opening a portal is a term that's often misinterpreted by the sci-fi element of popular culture. Scientifically speaking, a portal is not a mystical gateway to another dimension, as shown in the movies or on television. Instead, it refers to the potential creation of microscopic black holes during particle collisions. These phenomena, predicted by the same string theory, would be extremely short-lived and would not pose a threat to our existence, as the sensational news of the yellow press suggests. While in pop culture, portals may be portrayed as doors to alternate realities or times, in the world of high-energy physics, they represent an opportunity to observe and study conditions and particles that can barely exist in the natural universe. These experiments have the potential to open up new dimensions of physics, literally. By analyzing the particles produced by these collisions, scientists can gather evidence that either confirms these theories or sends them back to the drawing board. With its unprecedented ability to test these theories, the LHC acts like a giant microscope, magnifying the very fabric of the universe and helping us understand the fundamental principles that govern everything we see and everything we don't. Particle physics is constantly evolving, and each experiment and discovery pushes the boundaries of our understanding of the universe. From discovering fundamental particles to challenging the limit of physics, the achievements of this research center are monumental. At the center of such scientific advances is the discovery of the Higgs boson, a particle integral to the mechanism that gives mass to elementary particles. Discovered in 2012, this breakthrough confirmed a crucial part of the standard model of particle physics and won the 2013 Nobel Prize in Physics. The existence of the Higgs boson, often called the God particle, has answered fundamental questions about how particles acquire mass. This discovery was a triumph of theoretical physics. Also of note is the recent public release of the discovery of the Higgs boson by the CMS collaboration, which marks a significant commitment to open science and collaborative research. Transparency fosters a global scientific dialogue in which hypotheses can be rigorously tested and new theories can emerge from shared knowledge. This release, which includes the unique combined software developed to search for the Higgs boson, allows scientists around the world to explore the intricate details of this monumental discovery. The resulting likelihood function with nearly 700 parameters captures the complexity of the experimental data, offering a multi-dimensional representation that defies even the most sophisticated visualizations. This openness not only democratizes access to cutting-edge science, but also enhances the collective ability to validate and build on key findings. But the journey did not end there. CERN has played a key role in other significant discoveries, such as the isolation of antimatter and the detailed study of quark-gluon plasma, a state of matter thought to have existed just after the Big Bang. Another experiment called ALPHA has successfully trapped anti-hydrogen atoms, opening a new way to study the properties of antimatter. This pioneering work aims to answer the question of why the universe is made up mostly of matter, even though the Big Bang theory suggests there's an equal amount of matter and antimatter. Another cornerstone of CERN's research is the study of quark-gluon plasmas using the LHCb experiment. By studying quark-gluon interactions, scientists are delving into the study of the strong force, a fundamental force that holds atomic nuclei together. Each discovery at CERN not only adds a new layer to our understanding of particle physics, but also pushes the boundaries of what technology can achieve under such extreme conditions. These experiments require the precise coordination of hundreds of scientists and cutting-edge technology, reflecting the amazing collaboration of people around the world. As you may have realized by now, the LHC is not just a technology loop. It's a finely tuned experimental environment in which the most fundamental questions of physics are addressed. So, how does the Large Hadron Collider work? The process begins by feeding beams of protons into the collider from a chain of small gas petals. Each proton began its journey in a simple bottle of hydrogen, where electrons are stripped from it, leaving bare protons ready for acceleration. These protons pass through a series of gas petals, gaining energy at each stage until they finally arrive at LHC. Once in the collider, the proton beams are boosted to finite energy levels, reaching the 6.8 tera-electron volt mark during the latest 2024 launches. This intense energy is necessary for the protons to collide with sufficient force to decay into a range of subatomic particles, some of which may never have been observed before. The whole process takes place on a scale that's difficult to comprehend with everyday analogies, but we'll still try to explain the concept fully. 1 tera-electron volt is roughly equal to the kinetic energy of a flying mosquito. Thus, 6.8 TeV is akin to the total energy of about 6.8 flying mosquitoes. However, that energy is packed into a particle that is inconceivably smaller than a mosquito. The proton is a subatomic particle, meaning it's part of the nucleus of an atom and has a diameter of about 1 femtometer. By comparison, a mosquito is about 1/4 inch long. To visualize this difference, if a proton were the size of a pea, a mosquito would be the size of a large skyscraper. But all the energy of a moving skyscraper would be packed into such a small object. So let's continue. Of crucial importance in the whole process is the achievement of proton beam stability, a state when the beams are dense and well focused. The beams are carefully regulated or squeezed to ensure they collide in the detector at the point where they can be most effectively studied. This process involves precise control of the many magnets around the LHC ring that guide and focus the beams. The collider has already produced its first stable beams at unprecedented energy levels in 2024, marking the official start of this year's physics data collection season. The third year of LHC Run 3 promises 6 months of proton collisions with energies of 13.6 teraelectron volts at even higher luminosities than before, meaning more collisions for data gathering experiments. This phase will be followed by experiments with lead ions, providing a different set of conditions to study. Also this year, the ATLAS experiment has already achieved a milestone in particle physics by measuring the width of the W boson for the first time. This parameter, crucial for understanding the weak force carried by the W boson, was found to be 2202 mega electron volt, which agrees well with the predictions of the Standard Model. Moreover, at the forefront of investigating the fundamental asymmetries of our universe, the LHCb collaboration has made significant progress in understanding the complex interplay between matter and antimatter. In recent experiments, they have studied the behavior of the neutral D meson and neutral strange B meson, uncovering new layers of complexity in how these particles violate charge parity symmetry. The neutral D meson, consisting of a charm quark and an up antiquark, has shown a peculiar quantum quirk. It can spontaneously transform into its antimatter counterpart and back again. This phenomenon's been captured with unprecedented precision in recent datasets from the first 2 LHC runs. The current study aims to identify potential CP violations in these transformations, which may shed light on the predominance of matter over antimatter in our universe. Similarly, the neutral strange B meson, consisting of a bottom antiquark and a strange quark, showed time-dependent CP violations when decaying into quark-gluon plasma. This observation marks a significant advance, as it was achieved with statistical significance beyond the typical discovery threshold in particle physics. These results not only confirm the known behavior of these particles, but also open new avenues of research. With the LHC now operating at higher luminosities, future data could further refine these measurements, potentially leading to new physics beyond the Standard Model that could explain dark matter and matter-antimatter asymmetry. In the vast universe of information surrounding the Large Hadron Collider, many myths and sensational stories have taken root. Today we'll try to clear up these misconceptions and explore the real scientific picture going on deep beneath the surface. One common myth is that experiments at the collider can inadvertently produce black holes capable of consuming the Earth. Now, while the LHC can create tiny black holes, they are on the quantum scale and evaporate almost instantaneously through a process known as Hawking radiation. Stephen Hawking's theoretical predictions convince us that these microscopic black holes pose no danger. They provide a fascinating insight into gravitational forces, but are far from the end-of-the-world scenarios depicted in science fiction. Another dramatic claim is that the collider opens portals to other dimensions or causes catastrophic natural disasters. Such scenarios, although popular in movies and on television, are not supported by any scientific data. The LHC's primary mission is to test the predictions of theoretical physics, to study the particles and forces at work in the universe, not to disrupt the fabric of reality as we know it. CERN operates under strict safety protocols. Comprehensive checks and risk assessments are carried out regularly to ensure that all experiments are safe, not only for scientists, but also for the environment. And finally, stories of supernatural phenomena or secret experiments are completely unfounded. As a transparent scientific organization, its research is published and available to the global scientific community. The commitment to openness extends to public documentation, accessible databases, and collaborative projects across continents. As we continue our journey, we want to remind ourselves to remember to rely on proven facts and scientific research. As we delve into the theoretical underpinnings of multidimensional research at CERN, we are exploring concepts that push the boundaries of our understanding of the universe. These areas of physics consider the possibility that our universe may not be limited to the 3 dimensions of space and 1 of time that we experience every day. The idea of higher dimensions comes from theories such as string theory and superstring theory, which both suggest that particles are not zero-dimensional points, but rather one-dimensional strings vibrating in multidimensional space. These theories suggest the existence of up to 10 or 11 dimensions, which may help resolve inconsistencies between quantum mechanics and general relativity. In practice, researchers at CERN use the Hadron Collider to investigate these higher dimensions indirectly. One approach is to look for signs of particles that may exist only in these higher dimensions, or effects such as the formation of microscopic black holes. The search for extra dimensions is not just a quest for knowledge about the fabric of space. It also has practical implications for understanding the fundamental forces of nature, including gravity. If extra dimensions do exist, they may explain why gravity is much weaker than other fundamental forces. Beyond theoretical curiosity, the study of higher dimensions can lead to technological advances in fields such as quantum computing and materials science, as these concepts push the development of new technologies to detect and measure extremely small and fast phenomena. As we delve deeper into the uncharted frontiers of particle physics, a new CERN initiative, the Search for Hidden Particles Project, or SHIP, is poised to revolutionize our understanding of the cosmos. The ambitious project aims to detect elusive ghost particles that may hint at higher dimensions beyond our 3-dimensional space. The SHIP experiment is based on an innovative concept. Unlike traditional collisions at the LHC where particles smash into each other, SHIP will direct them toward a fixed target, increasing the probability of detection. The method is expected to be 1,000 times more sensitive than any existing equipment at CERN. These ghost particles, potentially constituting dark matter or other unknown aspects of dark energy, remain invisible under ordinary conditions because of their extremely weak interactions with ordinary matter. The implications of the discovery of such particles are profound and will probably change our fundamental theories of physics. Along with SHIP, plans are underway for a future circular collider, which should be a leap forward in particle collision technology. It is planned that this collider will reach its full potential by the middle of the 21st century and will push the boundaries of human technology and scientific research. Potential discoveries made at SHIP and the future circular collider could open new chapters in the history of our universe, from advancing our understanding of fundamental particles to creating new technologies. The implications to go far beyond particle physics, promising a glimpse into the very fabric of the cosmos and perhaps even into the higher dimensions that weave it together. As CERN continues to support its scientific achievements, the quest for knowledge is moving forward, promising a future in which the mysteries of the universe will be revealed one collision at a time.